But from an intuitive standpoint, it's basically anything that can be reasonably represented on a cursor grid. It's a very good question. Any other questions? All right. Okay. So this is called a V-cycle, what we have coded up. There is also this W-cycle. It looks a lot more complicated, like these kind of lines. Basically, but from a programming standpoint, it's actually very easy to change from a V-cycle to W-cycle. The only thing we need to do, let's remove this. The only thing we need to do is copy this line, paste it, and do this. We have now changed from a V-cycle to a W-cycle. So can somebody look at the change I have done and tell me what I have done? Like, what is the effect on the execution of the code? Right. Like in the line I just pasted, I used the previous solution of the error equation as the initial condition for the second call. So, but why? So, what is the more important thing is I did a second call, right, of the recursion. So now, every time I go down a level, the multigrid function is called twice as frequently. That's what we are showing here. So this whole thing is one W-cycle on the grid with H grid spacing. And here is a multi-grid cycle with 2H grid spacing. And there are two of these. I call that consecutively twice. And the second time, so the first time is my line 12, and the second circle is my line 13. Okay? And within each of these calls, as we are going down further by one grid, you see there are also two multi-grid cycle calls, two even cursor grid multi-cycle calls. And this 4H multi-grid is called now 4 times. At the causes level, because I'm not calling anything more, so it's at the causes level, we are not going to this if statement at all, right? So we are just one dot as a representation. So why sometimes we want to do this? We want to do this. I've only seen a W-cycle called in something at least in 2 dimensions, and most frequently in 3 dimensions. This is because the cost of solving the error equation on the cursor grid has been reduced by how much on a 3-dimensional grid? The grid is reduced by 8 times as you are going from doing something here to doing something here, right? So 8 times reduction in the grid size in 3D. That means doing something on the cursor grid is almost free, right, compared to doing the same thing on the finite grid. So if I'm able to solve the error equation more accurately, why not? If one multi-grid cycle is not going to be solving the error equation very accurately, then it makes sense to call the cost grid solution twice. Okay, so that's what a W-cycle means. Make sense? So we have we have used the under-relaxed Jacobi smoother. Okay, to do the pre-smoothing and post-smoothing. One of the things we see is that as we go to a coarse and coarser grid, the smoother seems to be doing a better and better job in solving the low frequency content. Right? Why is that the case? That has to do with the eigenvalue structure of the Jacobi iteration matrix in the Poisson's equation case. And that's one thing that makes multigrid so good at solving an equation is that a lot of these smoothers for a lot of equations we are interested in, they are much better in solving a smaller grid equation than a big grid equation. So one thing we can see is that let me close this file and let's also clear command window. Right. So let's just do it in 1D, a Jacobi iteration matrix, and take a look at its eigenstructure. So let's first take a look at n equal to what? N equal to 8, for example. Okay, and we are going to be constructing a matrix A that corresponds to the Poisson's equation. Dx equal to 1 divided by n. Okay, that's my dx. My A is equal to the diagonals. So A should be a 7 by 7 matrix, right? Because let's assume the boundary condition are Dirichlet boundary condition. What is 9? Right, it should be 9 points exactly, including the boundaries. And if we assume the boundaries are Dirichlet boundary condition, that means their values are already known, and the unknowns are 7, right? So A should be -2 times identity matrix of size n-1 divided by dx squared. So that's the diagonal parts. Plus, I'm going to say up once n-2, 1 and 1. So that's making a diagonal matrix that whose diagonal is shifted by 1. So let me do it slowly. So okay, so now let's open A. A is a 7 by 7 matrix with diagonals to be -2 times divided by dx squared. And let's add these upper diagonal parts divided by dx squared. So these are going to be putting 64s on the upper diagonal. So the ones are the entries of these of the non-zero elements. They are 64s. Because I'm dividing by dx squared. And the diag function makes a diagonal matrix, and this 1 means the diagonal is shifted upwards by 1. So if I do the same thing with -1 here, I'm going to put 64s on the lower diagonal part too. Okay, so that constructs the matrix I want. And if you look at the matrix and do an eigenvalue, take a look at the eigenvalues of A. It goes all the way from -246 to -9. Okay, so first of all, the eigenvalues are all negative and real. And also, let's look at the Jacobi iteration matrix. The Jacobi iteration matrix is minus the diagonal of A inverse, right? Which is something inverse times another matrix can be written as a backslash times the A minus the diag of A, right? That's the Jacobi iteration matrix. So let's call it R. Oh, sorry, diag of diag. Because diag so diag has when you apply diag to a matrix and a vector, it does different things. If you apply this to the matrix, it extracts the diagonal elements and put it as a vector. But if you apply it to vector, you make a diagonal matrix out of the vector. So diag of a diag means just take the diagonals of matrix A and then make a diagonal matrix only out of the diagonal entries. All right, so that's my iteration matrix R. And if you look at what R is, that's not very good. Oh, I also need the diag of A. Okay, so that's exactly the matrix we are envisioning, right? It has 0.5 on upper and lower diagonals. And if you look at eigenvalues of R, it ranges from minus 9.2 to 9.2, right? So these are what we want. It has to lie between minus 1 and 1. Otherwise, the Jacobi iteration is going to diverge. But it also goes somewhat close to 1 at both ends. And you're going to see, so what do you think if I make, instead of making n equal to 8, what if I make n equal to 124, as what we did in the 2D airplane case? There are going to be more points just because the matrix is larger, right? And the very largest and smallest values are going to be closer to 1. And what does that mean? That means the Jacobi iteration is going to converge much slower for a big entry. So let's do that. Dx equal to this. I'm going to repeat these, and I'll begin my construction of R, right? And I'm going to compute eigenvalues of R. Okay, and you can see this looks almost 1 because if I do format long, you're going to see these are not exactly 1, but very, very close to 1. So when you go to a coarser grid, you expect the Jacobi iterations to converge much faster. And what if we make n is equal to 2, as we were in the case at the coarsest grid? Let's repeat that. We get 1 eigenvalue equal to 0. Okay, that means if you don't do any on the relaxation, Jacobi would converge in how many steps? 1 step, right? The error is going to be reduced to 0 immediately. All right, if you do on the relaxation with the factor gamma, then the rate of convergence is 1 minus gamma to the nth power. So it means as long as you don't make gamma to be too small, it converges really fast. All right, any questions on the effect of Jacobi iteration or on the relaxed Jacobi iteration on the convergence of the iterative method for different grids?